The slope field method we studied just a moment ago turns out also to have important connections to how we could solve differential equations using computers in a way that is called numerical methods. What we're going to do here is take our idea of calculating the slope and see if we can automate it somehow. It seemed sort of wishy-washy. We would sketch the points we liked on the slope field before, and it wasn't particularly insightful or systematic. And Euler's method, notice the spelling here, this is German Euler, not Euler. This is Euler's method. It can be used as an alternative to the slope fields to generating a curve that satisfies an equation. The idea is, if you know where you are, so we have a starting point, and if you look at the slope field there, you know you can calculate the slope. Why? Because we have dy dx equals some function of our location. If we know where we are in time and space, or x and y, then we can calculate the slope. Euler's method just says, well, if I know where my slope is right now, let's follow that for a short time interval, or a short space interval x here, and then I'm going to be at a new point. And then I can recalculate. I can start here, find the slope, follow the slope for an interval. Then I can recalculate and get a new slope. And then I can follow that slope for the same interval. Should be the same interval, delta x. And then I'm at a new point. And then maybe I calculate the slope again. Now it's steeper again. Always returning back to our differential equation. When I say calculate the slope, I just mean plug x and y of my current point in to get dy dx values. And then we follow that. And again, same interval, delta x. And so on and so forth. Essentially, what we're doing is using the slope field idea, but instead of building a slope field everywhere, we just build the slope field at a sequence of points that are trying to build up a sketch of the graph. So we'd think of the graph going something like this, and we're getting an approximation to it using this algorithmic method. Here it is more formally. Notice we're going to put subscripts here because we're going to have x points and y points that change over iterations. So I is going to be the iteration. We compute the slope, and then we follow the slope for a step of delta x. And it's worth drawing the picture here. If we're at xi, yi, and we take a step of delta x, I'll make this very large to make it obvious. What's our new point? Our new point xi plus 1 is our old x plus delta x. Where does our other point go? Where does our y coordinate go? Well, what are the ingredients here? We've got a straight line which has slope delta y over delta x, but that slope is also being given by the differential equation, which is equal to dy dx. And so the delta y, how much do I go up or down when I take this step to the right? It's dy dx times, all we're doing is bring that delta x up and multiplying. So this is the slope from the differential equation. And this is the change in y that we get from before. And so yi plus 1 is yi plus delta y, or yi plus this dy dx times delta x. So aside from perhaps being confusing in terms of notation, all we're doing here is exactly what I laid out in the previous slide. We're finding a slope and we're following that slope for a step of delta x. And here's just the mathematical consequence of that if we actually want to calculate values. Let's do an example here. Consider this differential equation, dy dx equals x plus y, with initial condition, so we know our starting point. That's the key thing. We're being told we're going to start at y of 0, so x of 0, and y of 0.1. That's our starting point. Notice we have to tell you, if we want you to solve this directly, what the delta x step we're going to use is. So here's an example. X and y are given. the slope is x plus y. So all we do is add these two together and we get our slope value, just because this differential equation is fairly simple. We just add x and y. Now, the change in y that we expect is the slope times delta x. So the slope is here, then we have delta x, and that gives us a change in y of 0.01. Then what's our next step for this table? Well, our x goes up by delta x, and our y goes up by delta y. We just calculated the change, so we add that in here. Then we can do the same thing again. Okay, so I was at some point. I've now moved up a hair. Now, at that new point, I'm going to get a different slope. Our new slope is going to be x plus y, 0.21. And then I've got my slope at that point. I follow that slope. It's going to cause a change in y of, in this case here, 0.021. Because again, we have slope times delta x, or dy dx times delta x. And once again, we add delta x to this, we add delta y to this, and we get 0.0131. All right, we're at a new point. So we followed our graph to a new point. Now we do it again. So we add our slopes, add our x and y value to get a slope rather, and this will be, whoops. Misplaced a decimal there. That should be 0.131. So then this is 0.331. And 331. So we get a new increase again. 0.3164-ish. I'll stop at 3 decimals. And 0.464. We take that slope and multiply it by delta x. And we're going to get 0.04, 0.208, something like that. That's right. Nope. 0.21. 0.21. What am I doing? Give or take. All right. This box is what we're looking for, because this gives us a sequence of xi, yi's on, or approximately on, the graph of y of x. It gives us a sequence of points that, if we sketch them out, will follow very closely, not perfectly because we're approximating here, but very closely to the solution that we're looking for. Here's the zoomed in version. We started off at 0, 0.1, and then we took some steps. Now we didn't take a lot of steps, so let's just go back here a second. Notice our step size was 0.1 in x's, sorry. So we had 0.1 to 0.4, and by the end we were at 0.4, 0.2. So let's see how that ties into the slope field. 0.4, 0.21, and back here we were at 0.131, 0.11. All right. 0.131, 0.161 was about here and there. So these would be the points that we computed with Euler's method. And what we're seeing is a sketch of the solution that satisfies the slope field. This would be y of x solution beginning at the point 0, 0.1. That's not a bad idea. And we can see again, if you have any programming experience, how we could automate this procedure. No one really enjoys going through Euler's method by hand, even though that's how they used to do it back in the 1800s. But we can see that with a computer, we could automate the calculations on the previous page very easily. I have x, I have y, I calculate, increase. Have x, I have y, I calculate, increase. But for now, the important thing is to realize that there's an association between the slope fields that we saw earlier and the graph generated, the approximate graph generated using Euler's method. Now, just as a more general comment, would you say that the values for y of x, because remember these things are approximations, are they overestimates or underestimates of the real graph y? Think about that for a second. Well, how would you know? Well, I think the best way to recognize what's happening with the over versus underestimates is to look at the slopes that we started using. So we followed a slope to get to this point here. Let me try to draw this as straight lines. We followed a slope to get to this point here, and then we followed a steeper slope to get to the next point. What that means is that the slopes of y of x increase as we move from here to here, because we got a new slope at the next point. And we can see that basic shape here on the graph as well. As we move from left to right, the slopes get steeper. So what we missed is what the real graph should have done. It should have followed this initially. We had that slope right. But then it should have ended up a little bit higher, because the slopes of the real or exact y of x should increase over that interval. And so we get a curve. The real solution would be slightly curved up. We followed a straight line that used the lowest possible slope, and so we ended up below. So our y of x Euler estimates are underestimates of the real y values. Not bad underestimates, but still they're just a little bit below where they would be if we could have actually followed the slope field exactly. And that's worth knowing as well. You'll see some assignment problems that tie into that idea. I think that concludes our study of slope fields and Euler methods. We're going to look at techniques for solving these equations analytically. None of this approximation silliness anymore in the next lectures.